Hello there, and welcome to Sleepy Science Vault. There was a time before stars, before light, before any structure in the universe at all. A time when everything that exists was compressed into a state so dense, so incomprehensibly hot, that the laws of physics as we know them barely held together. And yet, even in that primordial chaos, something remarkable was already happening. At the smallest possible scales, the universe was not perfectly smooth. Tiny quantum fluctuations, variations so minute they existed at the edge of physical reality, were rippling through the fabric of space. These were not random accidents. They were the seeds of everything that would come to exist. Every galaxy, every star, every world circling a distant sun, all of it traces back to those almost imperceptibly small wrinkles in the early universe. The cosmos began expanding almost immediately, and it has never stopped. That expansion continues even now, carrying galaxies away from one another across distances so vast that light itself struggles to cross them. But in those earliest moments, expansion worked differently. A process called cosmic inflation stretched the universe at an extraordinary rate, and as it did, it amplified those tiny quantum fluctuations into something larger, pockets of space that were ever so slightly denser than their surroundings. Those dense regions would eventually become the birthplaces of galaxies. It is almost strange to think about. The largest structures in the known universe, collections of hundreds of billions of stars, all began from something smaller than anything we can see, or touch, or measure directly. Tiny clumps of matter, pulled gently together by gravity, slowly condensing over millions of years. But ordinary matter alone could not have done this on its own. Something else was needed. Dark matter makes up roughly 5 times more of the universe's total mass than all the normal matter combined. Atoms, molecules, planets, stars, gas clouds, everything we can see or detect with light, accounts for only a small fraction of what the universe actually contains. The rest is dark matter, invisible and silent, passing through ordinary matter as though it isn't there, detectable only through the gravitational influence it exerts on everything around it. And it was dark matter that built the first scaffolding of the cosmos. Computer simulations of the early universe, some of the most complex calculations ever performed, consistently show the same thing. Dark matter began clumping together first. Small concentrations formed, then pulled in neighboring concentrations, merging and growing into larger and larger structures over time. This process, known as hierarchical formation, built the invisible architecture of the universe piece by piece, from the smallest scales upward. What dark matter left behind was a kind of cosmic skeleton, a web of dense regions and filaments stretching across space, providing the gravitational wells into which ordinary matter would eventually fall. Without it, there would be no galaxies. Without it, there would be no stars, no planets, and no one looking up at the night sky wondering how any of this came to be. The very first structures to take shape were called protogalaxies, fragile, irregular clouds of gas beginning to collect within those dark matter concentrations. This happened within the first few 100 million years after the Big Bang, an astonishingly short time on a cosmic scale. Not all of these early clumps survived. Some were too loosely bound, too diffuse, too easily disrupted by the energy pouring through the early universe. Those transient structures simply faded, dissolving back into the surrounding gas, their brief existence leaving no trace. Only the ones that held together, only the ones where gravity was strong enough, and the conditions right enough, those became something more. And that is where the story of galaxies truly begins. Gravity is patient. It does not rush. It simply pulls, steadily and without rest, drawing matter toward matter across the silence of space. And in the early universe, that quiet persistence was enough to change everything. Within the dark matter concentrations that had begun to form, ordinary matter, primarily hydrogen and helium gas, started to follow. Slowly, over millions of years, enormous clouds of gas began to collapse inward under their own weight. As they fell, they condensed. As they condensed, they heated. And deep within the densest regions of these collapsing clouds, the first protogalaxies were taking shape. The process had a kind of elegant order to it. Gas fell toward the center of each collapsing structure, drawn by gravity into an ever-tightening core. Meanwhile, the dark matter arranged itself differently. Rather than concentrating at the center, it settled into a vast surrounding halo, a roughly spherical cloud of invisible mass that enveloped the entire system. That dark matter halo was not passive. It was the gravitational anchor around which everything else would organize. The gas at the center, the stars that would eventually form there, the entire visible galaxy, all of it was held in place by the quiet, unseen mass of the halo surrounding it. The smallest of these early dark matter halos contained the equivalent of roughly 1 million solar masses. By galactic standards, that is extraordinarily small. Our own Milky Way sits within a halo hundreds of times more massive. But 1 million solar masses was apparently enough. Enough to gather gas. Enough to compress it. Enough to push conditions toward a threshold that the universe had never crossed before. The ignition of the first stars. It happened approximately 100 million years after the Big Bang, a period astronomers sometimes call the cosmic dawn. Before this moment, the universe had been dark. Not dim, not faintly lit, but genuinely, completely dark. There were no stars anywhere. The cosmos was filled with gas and dark matter and the faint afterglow of the Big Bang itself, but no points of light. No sources of radiation. Nothing burning. And then, in scattered locations across the universe, the first stars switched on. These were not stars like our sun. The stars that formed in those earliest halos were almost certainly massive, some of them hundreds of times the mass of our sun, burning with an intensity that modern stars rarely approach. They formed from gas that was chemically simple, containing almost nothing except hydrogen and helium. Without heavier elements to help the gas radiate energy and cool more efficiently, these early clouds fragmented differently than gas clouds do today, tending to produce stars of enormous size rather than the smaller, longer-lived stars that are more common now. They were brilliant, and they were brief. Not long after this, galaxies began forming stars in earnest. By around 200 million years after the Big Bang, the process was already well underway in at least some regions of the universe. When we observe the most distant galaxies ever detected, those whose light has traveled for most of the universe's history to reach us, we are sometimes seeing galaxies whose stars were already 750 million years old at the time their light left them. Which means those stars formed even earlier, deeper in cosmic time, in an era we are only beginning to understand. The short lives of those first massive stars had consequences that echoed across billions of years. When a star far more massive than our Sun exhausts its fuel, it does not fade quietly. It explodes, a supernova of extraordinary violence, releasing more energy in moments than our Sun will radiate across its entire lifetime. Those first supernovae did something that would prove critical to the future of every galaxy in the universe. They forged heavy elements, carbon, oxygen, silicon, iron, and scattered them outward into the surrounding gas. In the language of astronomy, these elements are called metals, and before the first stars exploded, the universe contained almost none of them. The introduction of metals changed everything about how gas behaves. Metal-enriched gas can radiate energy far more efficiently than pure hydrogen and helium. It cools faster. And gas that cools faster can collapse more readily, fragment more easily, and form stars in a wider variety of ways. The supernovae of the first stars were, in a very real sense, preparing the universe for all the galaxies that would follow. The detailed properties of those first galaxies, their sizes, their shapes, the rate at which they formed stars, depended in subtle but profound ways on the physics of the gas itself. How efficiently it cooled. How quickly it collapsed. How it responded to the energy released by the stars forming within it. These are not simple processes. They involve interactions between gravity, pressure, radiation, turbulence, and chemistry all occurring simultaneously, across scales ranging from individual star-forming clouds to entire protogalactic systems. The complexity is immense. And at the heart of that complexity, the masses of the very first stars mattered enormously. A universe where the first stars were predominantly small would have evolved differently from one where they were predominantly enormous. The rate at which metals were produced, the energy deposited into surrounding gas, the way halos grew and merged, all of it was shaped by what those first stars were like. In many ways, understanding the first galaxies means first understanding the stars that lit them. For a long time, the details of this process were largely out of reach. The observational evidence was sparse, and the physics was too complex to work through with pencil and paper alone. But over the past few decades, something changed. Supercomputers, machines capable of performing trillions of calculations per second, made it possible to simulate the formation of galaxies in a way that had never been possible before. These simulations begin with the conditions of the early universe, as measured by instruments observing the faint remnant radiation of the Big Bang, and then run time forward. Gravity pulls matter together. Gas collapses. Stars form and explode. Energy flows outward. Dark matter halos grow and merge. And over simulated billions of years, structures emerge that look, remarkably, like the galaxies we observe in the real universe. It is one of the great triumphs of modern astrophysics, the ability to recreate, inside a machine, the birth of galaxies. Not perfectly, and not without assumptions that continue to be tested and refined, but well enough to reveal, in extraordinary detail, the processes that shape the universe we live in. The story of how galaxies are born is, in many ways, still being written. New telescopes reach deeper into the past. New simulations grow more sophisticated with each passing year. And with each discovery, the picture becomes a little clearer, a little richer, a little more astonishing than it was before. There is a threshold in the universe, a line that separates structures that flicker and fade from structures that endure. Not every dark matter halo becomes a galaxy. Not every collapsing cloud of gas produces something lasting. For a true galaxy to form, something specific has to happen first. The halo has to grow large enough. Astronomers have found, through both observation and simulation, that dark matter halos need to accumulate roughly 1 billion solar masses before conditions become favorable for sustained galaxy formation. Below that threshold, the process tends to stall. Gas may begin to collect, stars may even begin to form, but the system lacks the gravitational depth to hold on to its fuel. Energy released by young stars, ultraviolet radiation, supernova shockwaves, powerful stellar winds, can drive gas outward faster than gravity pulls it back. The halo is simply too shallow a well. The gas escapes, star formation sputters, and whatever structure had begun to take shape fades rather than grows. But once a halo crosses that threshold of 1 billion solar masses, the balance shifts. Gravity becomes strong enough to retain gas even against the energetic outflows of active star formation. Fresh fuel continues to fall inward. Stars continue to form. The galaxy sustains itself, building mass over time rather than losing it. That distinction, between a system that holds together and one that disperses, is the difference between a passing cloud and a galaxy. This requirement for a minimum mass is one reason the universe did not immediately fill with galaxies after the Big Bang. Dark matter halos had to grow first, and growth takes time. Halos accumulate mass by drawing in surrounding material and by merging with neighboring halos. The smallest halos formed earliest, but they needed time to build toward that critical threshold. The universe, in its earliest chapters, was engaged in a slow and patient process of assembly. And while that assembly was underway, the universe remained dark. It is difficult to fully appreciate what that darkness means. We are accustomed to a night sky scattered with stars, to galaxies visible through telescopes in every direction, to a universe that seems luminous and full. But for hundreds of millions of years after the Big Bang, there was none of that. The cosmos was filled with neutral hydrogen gas, a fog that absorbed almost all high-energy radiation, and within that fog, there was no light. No stars visible across cosmic distances. No galaxies glowing in the dark. Just gas, and dark matter, and the slow gravitational pull drawing them together. The moment that changed is one of the most dramatic transitions in the history of the universe. When the first true galaxies ignited, when enough massive stars had formed in enough places, they began flooding the surrounding universe with ultraviolet radiation. That radiation was energetic enough to strip electrons from hydrogen atoms, a process called ionization. And as more and more galaxies formed, the ionized regions around them grew and expanded, eventually merging into enormous bubbles of transparent, ionized gas stretching millions of light years across. This era is known as the epoch of reionization, and for a long time, astronomers assumed it had been a gradual, relatively quiet process, a slow clearing of the cosmic fog as galaxies steadily multiplied and their radiation spread outward. But as observations have improved, particularly in the last decade or so, the picture that has emerged is considerably more dramatic. Reionization appears to have been more explosive than expected, and it happened somewhat later in cosmic history than earlier models predicted. The fog did not simply thin and fade. It was burned away in powerful bursts, driven by concentrated populations of early galaxies pouring radiation into their surroundings. The universe's transition from dark to light was abrupt, uneven, and violent in ways that continue to surprise researchers. Those ionization bubbles, vast transparent regions carved out of the neutral hydrogen fog, are among the largest coherent structures ever identified in the observable universe. Each one was the product of an entire population of galaxies working together, their combined radiation overwhelming the surrounding gas across distances that dwarf anything in our local cosmic neighborhood. Standing at the edge of one of those bubbles, if such a thing were possible, you would be standing at the boundary between two completely different universes, one transparent and illuminated, the other dark and opaque. The first galaxies that drove this transformation were extraordinary objects. They formed from gas that was almost entirely hydrogen and helium, with only the faint traces of heavier elements scattered by the very first supernovae. Their chemical composition was as close to primordial as a galaxy can get, a direct reflection of the material produced in the first minutes after the Big Bang, largely unaltered by billions of years of stellar processing. The stars they contained were different from the stars we see today. The galaxies themselves were smaller, more irregular, more turbulent. They bore very little resemblance to the grand spirals and ellipticals that populate the modern universe. Yet they were the beginning of everything. By around 1 billion years after the Big Bang, a mark that astronomers use as a rough boundary in discussions of the early universe, true galaxies were established across the cosmos. They existed. We know this not just from theory, but from observation. Light that left those ancient galaxies nearly 13 billion years ago has been traveling through space ever since, and some of it has now reached us. The galaxies that emitted it are long gone in any recognizable form, transformed beyond recognition by billions of years of evolution. But their ancient light carries information about what they were, and that information is just now beginning to be decoded. For most of the history of modern astronomy, observing galaxies from that first billion years was essentially impossible. The light was too faint, too redshifted, stretched by the expansion of the universe into infrared wavelengths that ground-based telescopes struggled to detect. Hints existed. Distant objects were identified. But seeing into that earliest era with any clarity felt perpetually just beyond reach. And then the James Webb Space Telescope changed that. Webb was designed, in part, for exactly this purpose. Its massive mirror, its exquisite sensitivity to infrared light, its position far from Earth's atmosphere, All of it was optimized to look further back in cosmic time than any observatory before it. And when it began returning data, the results were stunning. Webb did not merely detect ancient galaxies. It observed galaxy formation itself, the actual process of early structures assembling, of gas condensing, of the first organized stellar populations taking shape in the young universe. For the first time in the history of science, human beings watched a galaxy being born. That is not a small thing. Generations of astronomers built careers on questions that could not yet be answered. Theorists constructed models and waited decades for instruments capable of testing them. And now, those instruments exist, and they are working, and they are sending back images and spectra that are rewriting our understanding of the early universe almost faster than it can be fully absorbed. What Webb has already revealed has surprised nearly everyone. Some early galaxies appear more massive, more organized, and more chemically evolved than models predicted they should be at such an early time. The universe, it seems, was building structure faster than we thought. Exactly why that is, whether our models need adjustment, whether there are physical processes at work that we have not yet accounted for, is an open and deeply exciting question. The first galaxies were not simply smaller, simpler versions of the ones we see today. They were something genuinely different, objects shaped by conditions that no longer exist anywhere in the observable universe, burning with a ferocity that the modern cosmos cannot replicate. Understanding them is not just an exercise in filling in the blanks of cosmic history. It is a window into a universe that was fundamentally unlike our own, governed by the same laws but operating in an entirely different regime. And the more we look, the more we find waiting there in the dark. The early universe was not a quiet place. It is easy, looking at the night sky, to imagine the cosmos as something serene and slow, stars drifting in the dark, galaxies turning at a stately pace across incomprehensible distances. And in many ways, the universe we live in now is relatively calm, at least by the standards of what came before. Because there was an era, billions of years ago, when the universe was building itself at a rate that makes today's cosmic activity look almost restful by comparison. In the young universe, stars were forming everywhere, and they were forming fast. The overall rate of star formation across the cosmos was roughly 10 times higher than it is today. 10 times more stars igniting per year, across the entire observable universe, than are being born in the present era. The fuel was plentiful, the conditions were favorable, and gravity was working with an urgency that the modern universe, older, more spread out, more depleted of raw material, simply cannot match. Even the smallest galaxies were participating. Dwarf galaxies in the early universe, systems far smaller and less massive than the Milky Way, were producing stars at rates 10 times higher than comparable small galaxies in our local cosmic neighborhood today. These were not minor contributors to the overall picture. They were extraordinarily active, pouring out radiation and seeding their surroundings with the products of stellar evolution at a pace that seems almost implausible when measured against modern galaxies of similar size. The young universe was not just building large galaxies quickly. It was building all galaxies quickly, from the grandest structures down to the smallest. The scale of early galaxy formation became dramatically clearer when the Hubble Space Telescope began looking into the deep universe. In surveys that pointed at small, seemingly empty patches of sky and collected light for days at a time, Hubble revealed a cosmos teeming with early galaxies. More than 500 young galaxies were identified in the early universe through these observations, a number that represented not a census of everything out there, but merely what was detectable within specific regions of sky and within the sensitivity limits of the instruments. The actual population of early galaxies was far, far larger. What those galaxies looked like was not what anyone raised on images of modern spirals and ellipticals might expect. They were small, considerably smaller than the large galaxies that dominate the universe today, including our own Milky Way. They had not yet had the time to grow through mergers and accretion into the massive systems we are familiar with. But their size was not the most striking thing about them. Their color was. Early galaxies were blue. Intensely, unmistakably blue, at least in terms of what their light reveals about their stellar populations. Blue light in a galaxy is the signature of young, massive, hot stars. Stars that burn brilliantly but briefly, consuming their fuel in millions rather than billions of years. The prevalence of blue light in early galaxies was direct evidence of their extraordinary star formation rates, entire populations of massive young stars blazing together, making these small systems some of the most luminous objects of their era relative to their size. Modern large galaxies, by contrast, tend toward redder tones, the light of older, cooler stars that have survived long after their more massive siblings burned out. The shift from a blue early universe to a redder modern one is, in a very real sense, the universe aging. The hot, fast-burning generation giving way to the slower, longer-lived stars that populate galaxies today. But color alone does not capture how different early galaxies truly looked. Their structure was nothing like the smooth, sweeping spiral arms or the graceful elliptical forms we associate with mature galaxies. Early galaxies were clumpy, irregular, turbulent. When astronomers began resolving their internal structure with sufficient clarity, first through Hubble and later through Webb, they found not the organized distributions of stars seen in modern systems, but collections of enormous star-forming knots scattered across the body of the galaxy in irregular patterns. These knots were extraordinary objects in their own right. Regions of intense, concentrated star formation, each one containing vast numbers of young stars packed into a relatively small volume, blazing with a combined luminosity that dwarfed anything found in typical star-forming regions today. To put it in perspective, the largest, most active star-forming regions in our current Milky Way, places like the Orion Nebula, are impressive by modern standards. But the clumps found in early galaxies were on a different scale entirely. They were not just more active. They were massively more active, forming stars at rates that modern star-forming regions cannot approach. These knots were the engines of early galaxy growth, the places where the raw material of gas and dust was being converted into stars at the highest possible efficiency. Why were early galaxies so clumpy? The answer lies, at least in part, in the conditions of the early universe itself. The gas in young galaxies was more abundant, more turbulent, and less stable than the gas in modern galaxies. When large amounts of turbulent gas are present, gravitational instabilities tend to produce large clumps rather than smooth distributions. The gas broke up into massive fragments, each fragment collapsing to form an intense pocket of star formation. The result was a galaxy that looked less like a structured system and more like a collection of brilliant, irregular fires scattered across a dark field. And yet, within that apparent chaos, there was also order. Observations of early galaxies have revealed something that surprised many astronomers. Even some of the most irregular, clumpy systems from the young universe showed signs of rotation. The gas and stars within them were not simply moving in random directions. There was a pattern, one side of the galaxy moving toward us, the other moving away, in the signature of an overall spin. It was not the smooth, well-organized rotation of a modern spiral galaxy. It coexisted with turbulence, with irregular motions, with the clumpiness that made these galaxies look so different from their modern counterparts. But the rotation was there. That combination of order and chaos is one of the more fascinating characteristics of early galaxies. They were not purely disordered. The seeds of organized galactic structure were already present, but they existed alongside conditions far more turbulent and energetic than anything typical in the modern universe. Watching an early galaxy was like watching something in the process of finding its shape, not yet settled, not yet mature, but clearly moving in a direction. Surrounding all of this activity, the star-forming clumps, the turbulent gas, the young stars blazing blue, were vast reservoirs of gas extending far beyond the visible boundaries of the galaxies themselves. This is true of galaxies in the modern universe as well. The stars and structures we can see with optical light represent only part of what a galaxy actually is. Beyond the visible disk or body of the galaxy, extending for hundreds of thousands of light years in some cases, lie enormous halos of gas, material that has been expelled by stellar winds and supernovae, or that has never yet collapsed into stars, or that is slowly raining inward as the galaxy draws it from the surrounding intergalactic medium. These gas reservoirs are the fuel tanks of galaxies. They represent the future, material that will, over billions of years, gradually fall inward, trigger new rounds of star formation, and contribute to the ongoing growth of the galaxy. In the early universe, these reservoirs were enormous and full, one reason why star formation rates were so high. There was simply more raw material available, and it was closer, and it was falling in faster. As the universe has aged, those reservoirs have been depleted. Gas that falls and gets converted to stars. Stars live and die and enrich the gas with heavy elements, but they also consume it. Over billions of years, the overall supply of cold, star-forming gas in the universe has declined. The cosmic star formation rate has dropped accordingly. The universe is not running out of material entirely. Star formation continues today, and will for billions of years yet. But it is a slower, more measured process than the furious construction that characterized the young cosmos. The early universe was, in the truest sense, a time of explosive growth. A time when the raw potential of the cosmos was being realized at maximum speed, when galaxies were assembling themselves with an energy and pace that the modern universe can no longer sustain. What we see around us today, The quiet spirals, the ancient ellipticals, the vast cosmic web of structures, is the mature product of that extraordinary early era. The fireworks have faded, but the universe they built remains. One of the quieter surprises to emerge from observations of early galaxies concerns not their size, or their star formation rates, or even their irregular shapes, but their chemistry. The first galaxies were chemically strange by modern standards. Carbon, which plays a fundamental role in the chemistry of the present-day universe, in the interstellar medium, in the formation of complex molecules, in the building blocks of life itself, was dramatically underrepresented in early galaxies. These systems showed extreme carbon deficits compared to what we observe in galaxies today. The reason traces back to where carbon comes from. It is forged inside stars, over time, and released into the surrounding gas when those stars die. In the earliest galaxies, stellar generations had not yet had enough time to enrich the surrounding environment. The universe was young, the stars were young, and the slow accumulation of heavier elements that would eventually produce a chemically rich cosmos had only just begun. That chemical poverty is a reminder of how genuinely different the early universe was, not just in scale or activity, but in the very composition of the material from which galaxies were made. Everything that makes the modern universe chemically complex and biologically interesting had to be built, slowly, across billions of years of stellar birth and death. And while that chemistry was developing, the galaxies themselves were growing in ways that astronomers have debated, refined, and gradually pieced together over decades of observation and theory. The question of how galaxies grow is, at its core, a question about process. Do large galaxies form all at once, collapsing from enormous clouds of gas in single dramatic events? Or do they assemble gradually, built up from smaller pieces that come together over time? For much of the 20th century, these two broad ideas competed for acceptance. And while the details remain an active area of research, the weight of evidence has settled fairly clearly on one side. Galaxies grow the hard way. They build themselves from smaller components, piece by piece, over billions of years. This picture, known as hierarchical formation, is supported by observations across a wide range of cosmic epochs. Small dark matter halos form first and merge into larger ones. Small galaxies form within those halos and are gradually drawn together by gravity, colliding and combining into progressively larger systems. The large galaxies we see today, including our own Milky Way, are the accumulated products of countless mergers and interactions stretching back to the earliest structures in the universe. Galaxy collisions were not rare events in the early universe. They were common. Extraordinarily so. In the young cosmos, where galaxies were smaller, more numerous in dense regions, and moving within a space that was far less expanded than it is today, encounters between galaxies happen with a frequency that the modern universe rarely matches. Two galaxies approaching each other do not collide the way solid objects do. They are mostly empty space, and their stars pass through one another without directly hitting. But gravity does its work regardless. Tidal forces distort both galaxies during a close passage. Gas clouds are compressed, triggering bursts of star formation. Stars are flung into new orbits. And if the encounter is close enough and slow enough, the two systems eventually lose enough energy to their mutual gravitational interaction that they spiral together and merge into a single, larger galaxy. The result of a major merger between two large spiral galaxies is typically an elliptical galaxy, a rounder, more diffuse system with a more randomized distribution of stellar orbits than the organized disk from which the spirals began. This is one reason why the universe contains so many elliptical galaxies, particularly in dense environments where mergers have been most frequent. But before mergers had transformed the population, the early universe was dominated by a different kind of galaxy. Observations consistently show that among the earliest recognizable galactic structures, spirals were far more common than they are today in comparable environments. The young universe, for all its turbulence and irregularity, was producing spiral galaxies, systems with rotating disks and organized internal structure, in impressive numbers. That may seem counterintuitive given how chaotic early galaxy formation appears in other respects. But the conditions that favor disk formation, particularly the rotational momentum of infalling gas, were present from very early times. Spirals, it turns out, are in some sense the default galaxy. They require merging and disruption to be transformed into something else. As galaxies grew through mergers and accretion, they passed through a series of intermediate stages, systems that were neither the small, clumpy protogalaxies of the earliest universe nor the fully mature galaxies of the present day, but something in between. For a long time, these intermediate objects were poorly understood, largely because they were difficult to observe at the distances involved. But in recent years, a number of galaxies have been identified that appear to represent exactly these transitional states, objects that serve as missing links in the story of galaxy evolution, showing the process of assembly caught mid-stride. These discoveries are particularly valuable because they provide direct observational constraints on theories of galaxy growth. A model that predicts how galaxies should evolve can be tested against what these transitional systems actually look like, their sizes, their star formation rates, their chemical compositions, their structures. Every such object found and characterized adds another data point to a picture that is still being assembled. Some of the most remarkable recent observations concern galaxies at the very edge of what current telescopes can detect, systems so distant that their light left them when the universe was only a small fraction of its current age. Among these are ultra-distant galaxies whose light has been traveling for 13.3 billion years before reaching us. These are not merely old galaxies. They are windows into a cosmic era so remote that the universe was almost unrecognizably young when they existed. Studying them requires pushing instruments to their absolute limits, and the information they return is correspondingly precious. What these observations reveal, time and again, is that the universe was building structure earlier and faster than many models initially predicted. Galaxies at extreme distances are sometimes larger, more chemically evolved, and more organized than they theoretically ought to be given how little time had passed since the Big Bang. This persistent tension between observation and prediction has driven significant revisions in models of early galaxy formation and continues to motivate new research. The story of galaxy growth is also, inevitably, a story about galaxy clusters, the largest gravitationally bound structures in the universe. Individual galaxies do not generally exist in isolation. They are social objects, drawn together by gravity into groups, and groups into clusters, and clusters into the vast superclusters and filaments of the cosmic web. The Milky Way itself belongs to a modest collection called the local group, which in turn sits near the edge of a much larger structure called the Virgo supercluster. But in denser regions of the universe, galaxy clusters can contain hundreds or even thousands of individual galaxies, all bound together within a common dark matter halo and swimming in a bath of hot, diffuse gas. These clusters are not static. They grew, like individual galaxies, through hierarchical assembly, smaller groups falling together over time into progressively larger structures. And in some cases, the ancestors of present-day clusters can be identified in the distant universe as early concentrations of young galaxies, dense knots in the cosmic web where the future structure is already beginning to take shape. One remarkable cluster was found to have formed when the universe was only about 7% of its current age. 7%. The universe today is approximately 13.8 billion years old, which means this cluster was already assembling when the cosmos was barely a billion years old. At that epoch, large-scale structure was still in its early stages everywhere. For a cluster to have formed so early requires an unusually dense initial concentration of dark matter, a region of the early universe that was ahead of the curve, building structure faster than its surroundings. These early clusters are of particular interest because they may represent the environments in which some of the most massive modern galaxies were born. The dense conditions within a young cluster accelerate galaxy evolution, mergers happen more frequently, star formation can be more intense, and the galaxies that survive within the cluster are shaped by their environment in ways that isolated galaxies are not. Several lines of evidence suggest that the large elliptical galaxies found at the centers of modern clusters, some of the most massive galaxies known, trace their origins back to exactly these kinds of early, dense protocluster environments. In a sense, the ancestors of the Milky Way and galaxies like it may have passed through eras of dense clustering in the distant past, or may have grown through the merger of systems that did. The history written in the stars of any given galaxy contains, encoded within it, a record of the interactions and mergers and environmental influences that shaped it across cosmic time. Reading that record is one of the central challenges of modern astrophysics. And with each new observation, each distant galaxy resolved, each cluster mapped, each missing link identified, the story becomes a little more complete, a little more detailed, and a little more extraordinary than it seemed before. Something has been quietly unsettling the standard models of cosmology for the past several years, and it begins with 6 galaxies. When the James Webb Space Telescope turned its instruments toward the deep universe and began returning its earliest science data, researchers expected to find what theory predicted: small, faint, relatively simple galaxies struggling to form in the young cosmos. What they found instead, in those first observations, were 6 massive galaxies that had no business being there. Not in the sense that their existence violated any fundamental law, but in the sense that they were far too large, too well developed, and too rich in stellar mass to have formed in the time available according to prevailing models of galaxy formation. These galaxies existed at a point when the universe was only a few 100 million years old. Building galaxies of their mass in that time frame would require star formation rates so extreme, sustained for so long, that they push against what current physical models consider plausible. Some researchers have suggested that our understanding of early star formation efficiency may need revision. Others have proposed that certain assumptions built into cosmological simulations require adjustment. A few have raised more radical possibilities. The debate is ongoing, and the answers are not yet settled. But the discovery carries a clear message: the universe matured faster than we thought. Structure formed earlier, on larger scales, with greater efficiency than our models predicted. The early cosmos was not gradually assembling itself in an orderly fashion. It was, in at least some regions, building at a pace that continues to challenge explanation. This is not a failure of science. It is science working exactly as it should, observations pushing theory straining to accommodate new data, and the resulting tension driving deeper understanding. But it is a reminder that the universe is under no obligation to conform to our expectations, and that the story of galaxy formation is still being revised in fundamental ways. With that in mind, the question of how different types of galaxies form becomes not just a matter of classification, but a genuine window into the physical processes that shape the cosmos. Walk through any large survey of galaxies and the variety is immediately striking. Some galaxies are flat, rotating disks with graceful spiral arms winding outward from a central bulge, organized, structured, still actively forming stars. Others are smooth, rounded clouds of older stars with little ongoing star formation and no obvious disk structure. Others still are irregular, asymmetric, neither spiral nor elliptical, often showing signs of recent disturbance or interaction. These broad categories are not arbitrary. They reflect real differences in history, in environment, and in the physical processes that governed each galaxy's formation and evolution. The classification system most familiar to astronomers, the one still used as a foundational reference today, was developed in the 1920s by Edwin Hubble. The Hubble sequence, as it is known, arranges galaxies along a diagram that runs from ellipticals of varying roundness on one end, through a transition zone of lenticular galaxies, and then branches into two tracks of spirals, ordinary spirals and barred spirals, on the other. Irregular galaxies sit outside the main sequence, a catch-all for systems that do not fit neatly into the other categories. Hubble's original intention was purely descriptive, a way of organizing the observed variety of galactic forms into a coherent framework. But over the decades, his sequence came to be interpreted, sometimes incorrectly, as an evolutionary track, with galaxies moving from one type to another over time. The modern understanding is considerably more nuanced. Galaxy types do change over time, but not in a simple linear progression. The path a galaxy takes depends on a complex interplay of initial conditions, environment, and the specific events, particularly mergers, that punctuate its history. At the heart of the distinction between spirals and ellipticals lies a question of timing. How quickly did a galaxy convert its gas into stars? Galaxies that formed stars relatively slowly, spreading the process over billions of years, tended to develop and maintain rotating disks, the structures we associate with spirals. When gas falls into a dark matter halo with significant rotational momentum, it naturally settles into a disk shape, and stars that form within that disk inherit its rotation. As long as the disk is not too severely disrupted, it persists and grows, producing the spiral patterns driven by density waves rippling through the rotating stellar population. Spiral galaxies are, in a sense, galaxies that took their time, building themselves gradually, maintaining their fuel supply over long periods, sustaining star formation across billions of years. Elliptical galaxies tell a different story. The leading picture of how giant ellipticals form involves major mergers between large galaxies, collisions violent enough to completely disrupt the disk structures of both participants. When two spiral galaxies of comparable mass collide and merge, the organized rotational motion of their stellar disks is scrambled. Stars are flung into new, more randomized orbits. The result, after the merger has settled and the system has reached a new gravitational equilibrium, is a rounder, more diffuse galaxy in which stars move in a variety of directions rather than sharing a common rotation. That is the structure of an elliptical. But the story of elliptical formation has an additional layer of complexity. Observations consistently show that the central bulges of spiral galaxies, the dense, rounded concentrations of older stars at the center of spiral disks, formed before the disks themselves. In other words, the inner regions of what would become spiral galaxies assembled quickly, in an early burst of rapid star formation, and the extended disk grew around them later, more gradually. This sequence, bulge first, disk second, implies that even spirals have an early, rapid phase of growth at their cores, one that shares more with elliptical formation than with the slow disk building that characterizes most of a spiral's subsequent history. Elliptical galaxies, particularly the giant ellipticals found at the centers of large clusters, likely underwent that early rapid phase on a much larger scale, converting enormous amounts of gas into stars quickly and then growing further through successive mergers. Their stellar populations are consequently old, most of their stars formed long ago, and star formation has since largely ceased. They are, in a very real sense, finished objects, their active histories largely behind them. Spiral galaxies, by contrast, are still in process. Still forming stars, still maintaining their disks, still drawing in gas from their surroundings. They are the ongoing chapters of galactic evolution, while ellipticals represent, in many cases, a kind of conclusion. Irregular galaxies occupy a different position in this picture. Many of them are irregular precisely because they are in the middle of something, a merger not yet complete, a close interaction with a neighbor that has distorted their structure, or simply a system that has not yet settled into a stable form. In the early universe, irregular morphologies were far more common than they are today, reflecting the turbulent, merger-rich conditions of that era. As the universe has aged and interactions have become less frequent, more galaxies have had the time and the undisturbed conditions necessary to develop stable, organized forms. Among all the galaxies we might study, one holds a particular significance simply because we live inside it. The Milky Way began forming approximately 13.6 billion years ago, so early that the universe was only a few 100 million years old at the time. In cosmic terms, it is one of the older galaxies in the local universe, its origins reaching back nearly to the dawn of galaxy formation itself. Tracing its history is an exercise that combines observations of the most distant ancient galaxies with detailed studies of the stars in our own galactic backyard, using the chemical and kinematic signatures written into those stars to reconstruct the sequence of events that built the system we inhabit. In its earliest form, the Milky Way was nothing like the sweeping barred spiral it is today. The initial structure from which it grew was a roughly spherical cloud of gas, an extended, slowly rotating protogalactic cloud settling within a dark matter halo. There was no disk yet, no spiral arms, no bar at the center. Just a diffuse sphere of primordial gas, beginning the long process of collapse and star formation that would, over billions of years, build the galaxy we call home. The stars that formed in those earliest stages of Milky Way history are still with us. Some of the oldest stars in the galaxy, found predominantly in the central bulge and in the ancient stellar halo that surrounds the disk, date back to within the first billion years of cosmic history. They are living relics of the galaxy's formation, carrying in their chemical compositions a record of the conditions under which they were born. By studying these stars in detail, measuring their abundances of different elements and tracing their orbital motions through the galaxy, astronomers can read the early chapters of the Milky Way's biography with a directness that is not possible for any other galaxy. It is a remarkable thing to consider. The history of the universe, written in light reaching us from billions of light years away, is also written in the stars overhead, in the ancient light of suns that formed when the Milky Way itself was young, and that have been burning ever since, patient witnesses to everything that has followed. The oldest stars in the Milky Way did not form in the disk we see today. They formed earlier, in a different kind of structure entirely. Before the Milky Way had a disk, before it had spiral arms or a bar or any of the organized features we associate with it now, it had a halo. A vast, roughly spherical cloud of dark matter and gas surrounding what would become the galaxy's center, within which the earliest stars began to ignite. These halo stars, along with the stars packed into the ancient globular clusters that orbit the Milky Way in long, looping paths far above and below the disk plane, represent the galaxy's first generation, objects that formed in the initial, rapid collapse of the protogalactic cloud, before the disk had assembled at all. And that collapse was fast. Not gradual, not drawn out over billions of years in the way that subsequent disk formation would be, but rapid by galactic standards, a relatively swift infall of gas toward the gravitational center of the system, compressing material and triggering star formation in a burst that populated the halo and built the central bulge before the slower, more organized process of disk formation had properly begun. The evidence for this rapid early collapse is written in the chemistry of halo stars. Their compositions reflect the products of only the earliest stellar generations, with patterns of elemental abundances that point to star formation happening quickly, in a dense early environment, before the slower processes of chemical enrichment had time to play out. The thick disk of the Milky Way, a somewhat puffier, older stellar population that sits above and below the thin disk where most of the galaxy's current star formation occurs, tells a different story. Its stars are older and more chemically distinct from the thin disk population, and for a long time their origin was debated. The picture that has emerged from increasingly detailed stellar surveys points toward a dramatic event, a collision. Early in the Milky Way's history, a significant merger with another galaxy heated and thickened what had been a thinner disk, scattering stars into the more dispersed distribution we now observe as the thick disk. The galaxy we live in today was shaped, in part, by a collision billions of years in the past, one that left its signature not in any single visible scar, but in the kinematic and chemical properties of an entire stellar population. At the center of all of this, at the center of the Milky Way itself, sits something that would have seemed almost mythological to astronomers of an earlier era. A black hole 4 million times the mass of our Sun, compressed into a region smaller than our solar system, sitting quietly at the galaxy's core. It is called Sagittarius A*, and for most of its existence it has been relatively inactive, not currently consuming material at any dramatic rate, not powering the kind of luminous activity seen in the centers of more active galaxies. But its influence on the surrounding region is profound, and its presence raises questions that go far beyond any single galaxy. Because Sagittarius A* is not unusual. It is the rule, not the exception. Astronomers now understand that supermassive black holes, objects ranging from millions to billions of solar masses, reside at the centers of virtually all large galaxies. Not some of them. Most of them. The Milky Way has one. Andromeda has one. Every large elliptical galaxy examined in sufficient detail has one. The universe is, it turns out, full of these objects, one per major galaxy, sitting at the center of each system like an anchor point around which everything else is organized. This near-universal presence is not a coincidence. Supermassive black holes and their host galaxies did not develop independently and then happen to end up together. They grew together, influenced each other, and shaped each other's evolution in ways that researchers are still working to fully understand. The relationship between a galaxy and its central black hole is one of the most important and most actively studied topics in modern astrophysics. When a supermassive black hole is actively feeding, drawing in gas from its surroundings, it releases extraordinary amounts of energy. Not in the form of matter falling into the black hole silently, but in the form of radiation and powerful jets of material that blast outward from the region just outside the black hole's event horizon, driven by the intense magnetic and gravitational forces at work there. These jets and radiation fields can reach far out into the galaxy, heating the surrounding gas, driving powerful outflows, and in some cases completely suppressing star formation across the entire system. A black hole sitting at the center of a galaxy can, when active, effectively turn the galaxy off, shutting down the very star formation that built the galaxy around it. This feedback process is now understood to be a critical ingredient in galaxy evolution. Without it, simulations of galaxy formation produce galaxies that are far too massive, too star-rich, too different from what we observe. The black hole acts as a regulator, periodically releasing energy that heats the gas and prevents it from collapsing into new stars too rapidly. In this sense, the supermassive black hole does not merely live inside a galaxy. It helps determine what kind of galaxy it becomes. How these black holes themselves formed remains one of the deepest open questions in astrophysics. They are too massive to have grown simply from the collapse of individual stars, at least within the time available in the early universe. Something more must be involved, whether the direct collapse of enormous gas clouds, or the rapid merging of many smaller black holes in dense early environments, or some other process not yet fully characterized. A galaxy known informally as the Infinity Galaxy has provided one of the most tantalizing observational clues yet found. Its structure and properties have been interpreted as evidence bearing directly on the question of how supermassive black holes are born, not grown from smaller predecessors over long timescales, but formed through a more direct, dramatic process in the early universe. The details remain the subject of active analysis and debate, but the finding has added important observational weight to theoretical ideas that had previously lacked direct support. Against this backdrop of formation and growth and regulation, it is important to hold on to a point that might otherwise get lost. Galaxies are not static. They are not finished objects sitting unchanged in the dark. They are dynamic, evolving systems, constantly exchanging material with their surroundings, occasionally colliding with neighbors, being shaped by internal processes and external influences in ways that continue across their entire lifetimes. Even today, billions of years after the peak of cosmic star formation, galaxies are still changing. New galaxies are still forming in regions of the universe where conditions allow, where gas is still cool enough and dense enough to collapse into new systems. The universe has not finished building itself. It is older now, and slower, and the rate of new construction is a fraction of what it once was. But the process has not stopped. And in our own cosmic backyard, the evidence of ongoing galactic change is not abstract. It is visible. The Sagittarius Dwarf Galaxy, a small satellite galaxy orbiting the Milky Way, is currently being torn apart. Not in some distant future scenario, but right now, in the present epoch of cosmic history. The Milky Way's gravitational tidal forces are stronger at the near side of the Sagittarius dwarf than at its far side, and that difference in gravitational pull is gradually stretching and disrupting the smaller galaxy. Its stars are being pulled away from their original system and drawn into long, looping streams that wrap around the Milky Way in great arcs, threading through the galactic halo like ribbons of ancient starlight. This process is called galactic cannibalism, and it is not an unusual event. It is how large galaxies grow. The Milky Way has consumed smaller companions before, and the chemical and kinematic signatures of those past mergers are encoded in the stars of the halo and the thick disk, the same thick disk whose origin traces back to a collision long ago. Each absorbed galaxy leaves a mark. Each tidal stream is a kind of fossil, a record of a smaller system that once existed independently and no longer does. The Sagittarius dwarf will not survive as a distinct galaxy. Over the next few billion years, its remaining cohesion will be stripped away, its stars dispersed into the Milky Way's halo, its identity erased. It will become part of us, absorbed into a galaxy that has been quietly growing through exactly this kind of consumption across most of its history. There is something profound in that image. Not violent, exactly, though tremendous forces are at work. More like an inevitability, the natural outcome of gravity operating across time. Small things drawn toward large things. Boundaries dissolving. The universe continuing its patient work of assembly, one disrupted dwarf galaxy at a time, building the Milky Way into something slightly larger, slightly richer than it was before. The Sagittarius dwarf is not the first. Astronomers have identified the remnants of at least 12 smaller galaxies that the Milky Way has consumed across its long history, 12 distinct systems that once existed as independent structures, each with its own stars, its own dark matter halo, its own trajectory through space, and each now folded into the fabric of the galaxy we call home. Their identities are gone, but their signatures remain. Streams of stars with matching compositions and orbital characteristics trace the paths of ancient mergers, ghost outlines of galaxies that no longer exist as such, preserved in the motions and chemistry of stars now belonging to the Milky Way's halo. 12 is almost certainly an undercount. The techniques used to identify these past mergers are powerful but not exhaustive, and the halo is vast. As surveys grow more complete and analytical tools more sophisticated, the number of identified past mergers tends to grow. The Milky Way's history of consumption is likely richer than current data fully captures. Some of the evidence is hidden in plain sight, in objects that have been studied for centuries without their true nature being recognized. The Milky Way is surrounded by roughly 150 globular clusters, dense, spherical collections of hundreds of thousands to millions of stars, orbiting the galaxy in long paths that carry them far above and below the disk. For most of the history of astronomy, globular clusters were treated as a distinct category of object, fundamentally different from galaxies. But closer examination of the largest and most massive globular clusters has revealed something unexpected. Some of them, including Omega Centauri, the largest globular cluster associated with the Milky Way, show properties that are difficult to explain if they formed as ordinary globular clusters. Their stars span a range of ages and chemical compositions far wider than typical clusters, suggesting a more complex formation history. The leading interpretation is that these large, unusual globular clusters are not clusters at all in the traditional sense. They are the stripped nuclei of dwarf galaxies, the dense central cores of small galaxies that were pulled apart by the Milky Way's tidal forces long ago, their outer stars dispersed into the halo while their compact centers survived as what we now observe. If that interpretation is correct, and the evidence supporting it has grown considerably in recent years, then some of the most ancient and familiar objects in the sky are relics of galaxies the Milky Way destroyed billions of years ago. Ancient nuclei, preserved while everything around them was scattered to the winds of galactic tides. The process continues. Among the galaxies currently in the Milky Way's gravitational influence, one in particular is approaching a fate similar to the Sagittarius dwarf. The Canis Major dwarf galaxy, a small, irregular system whose stars are already partially dispersed into a ring-like stream around the Milky Way's outer disk, is expected to complete its merger with the Milky Way in roughly 1 billion years. On a human timescale, that is an incomprehensible length of time. On a cosmic one, it is not so far away. The Milky Way's history of absorption is not merely a past phenomenon. It is an ongoing one, with future chapters already written in the orbital mechanics of nearby companions. The Milky Way is not exceptional in this regard. When astronomers survey the histories of massive galaxies in general, systems of comparable or greater mass, the evidence points consistently in one direction. Nearly all massive galaxies have undergone at least one major merger in their past. Some have undergone several. The growth of large galaxies through the consumption of smaller ones is not a side process or an occasional occurrence. It is one of the primary mechanisms by which the universe builds its largest structures. A massive galaxy that has never experienced a significant merger would be the unusual case, the outlier, the object requiring special explanation. This understanding reframes how we think about the galaxies around us. Every large galaxy visible in the night sky carries within it the dissolved remains of smaller systems. Every one of them has a history of collision and consumption that stretches back billions of years. What we see as a single, coherent object is, in a deeper sense, a composite, an accumulation of many smaller histories, layered together by gravity and time. Yet for all the drama implied by the word collision, the actual experience of two galaxies merging is far quieter at the level of individual stars than one might imagine. When two galaxies collide, the vast majority of their stars do not collide with one another. This might seem counterintuitive, two objects passing through each other, their stars appearing to fill the same space simultaneously, and yet virtually none of those stars making direct contact. The reason lies in the extraordinary emptiness of galaxies. Stars are so small relative to the distances between them that even within the densest regions of a galaxy, the actual volume occupied by stars is a vanishingly small fraction of the total. If the Sun were the size of a grain of sand, the nearest star would be several kilometers away. Scale that up and distribute it across a galaxy of hundreds of billions of stars, and the result is a system that is almost entirely empty space. When galaxies merge, what interacts most dramatically is not the stars but the gas. Gas clouds collide and compress, triggering intense bursts of star formation. Tidal forces distort the stellar distributions and create long streamers and bridges of stars stretched between the merging systems. Gravitational dynamics scramble orbits and reshape structures over hundreds of millions of years. The process is violent in its effects on galactic architecture, but the stars themselves pass through one another's galaxies like ghosts, largely untouched. The transformed galaxy that eventually emerges from a major merger is genuinely new, not simply the sum of its parts, but something reorganized, reshaped, and in many cases fundamentally different in structure and behavior from either of the galaxies that produced it. And yet, even now, in a universe that is billions of years old and far past the peak of its galaxy-building activity, the story of galactic birth has not entirely concluded. The youngest known galaxy formed approximately 500 million years ago, recent, in cosmic terms, given that the universe is nearly 14 billion years old. Galaxy formation, it seems, has a long tail. The conditions that give rise to new galaxies were most common in the early universe, but they have not entirely ceased. In regions where gas remains cool and dense enough, where the necessary concentrations of dark matter are present, new galaxies can still emerge. The universe is old but not finished. In the most distant reaches of the observable universe, recent observations have returned results that continue to challenge and revise our understanding of early galaxy formation. A galaxy designated JADES GSZ 14-0, one of the most distant objects ever spectroscopically confirmed, contains something that surprised researchers: oxygen. Not a trace amount, but oxygen at a level indicating that significant stellar processing had already occurred. Oxygen is forged inside stars and released when they die. For a galaxy this ancient to contain detectable oxygen means it had already lived through multiple generations of stellar birth and death, had already accumulated the products of stellar evolution, far earlier than models comfortably predicted. The universe was chemically enriching itself faster than expected, in the same way it was building mass faster than expected. The theme recurs. Another distant galaxy, known as MOM-Z 14, has added a different kind of surprise. Its spectrum reveals elevated levels of nitrogen, an element whose abundance, in a galaxy this young, points toward extraordinarily intense and concentrated star formation in the recent past. Nitrogen at high abundances tends to be produced in specific stellar environments, and its presence in MOM-Z 14 suggests that the galaxy had recently gone through a phase of star formation so extreme that it enriched the surrounding gas with nitrogen at a rate the typical star formation history cannot easily account for. MOM-Z 14 had also done something else. It had cleared the surrounding hydrogen gas, ionized and pushed aside the neutral fog that typically surrounds galaxies in the early universe, carving out a transparent bubble in the intergalactic medium around itself. This is direct evidence of the reionization process in action, observed not as a statistical property of the universe but as the specific, localized effect of one very active early galaxy on its immediate surroundings. The galaxy was not merely forming stars. It was reshaping the universe around it, burning away the fog and letting light escape into the wider cosmos. Each of these distant, ancient galaxies is a data point in a picture that is still being assembled. Each one carries information about conditions and processes that no longer exist anywhere nearby, about an era of cosmic history that shaped everything that followed but that can only be studied at a remove of billions of light years and billions of years. Every observation is a message from the deep past, and every message is teaching us something new. The universe built its galaxies with extraordinary speed and extraordinary violence in those early eons. It has been refining them, growing them, merging them, and occasionally building new ones ever since. And we, living inside one of them, looking out through its disk of stars at the wider cosmos, are only now beginning to read the full account of how it all began. Among the many open questions in galaxy formation, one of the most visually compelling concerns those clumpy, irregular early galaxies, the ones observed in deep fields, riddled with massive star-forming knots, turbulent and asymmetric and so different from the organized spirals and ellipticals that populate the modern universe. The question is straightforward to ask and genuinely difficult to answer: how do you get from one to the other? The transition from a clumpy, irregular protogalaxy to a structured, stable spiral or elliptical is not something that has been directly observed in full. We see early galaxies in one state, and we see modern galaxies in another, and between those two snapshots lies billions of years of evolution that must be reconstructed rather than watched. Simulations suggest various pathways. The clumps within an early galaxy may gradually migrate toward the center under dynamical friction, feeding the growth of a central bulge while the surrounding disk slowly organizes itself. Alternatively, many clumps may be transient, forming rapidly, disrupted by stellar feedback before they can migrate, and replaced by new ones as gas continues to flow in. The relative importance of these two scenarios, and the conditions that determine which one dominates, remain actively debated. What is clear is that the transformation is real, and that it happened on a large scale across cosmic time. The universe went from being populated predominantly by irregular, clumpy systems to being populated predominantly by structured spirals and ellipticals. Understanding exactly how that transformation occurred, what physical processes drove it, on what timescales, and under what conditions, is one of the central unresolved problems of modern extragalactic astronomy. Part of the complexity arises from the fact that star formation itself can be triggered in fundamentally different ways. A galaxy does not need an external disturbance to form stars. Given sufficient cold gas and the right internal conditions, star formation can proceed entirely from within, driven by the natural gravitational instabilities of the disk, by turbulence, by the slow infall of gas from the surrounding halo. This is the internal pathway, the one that sustains the quiet, ongoing star formation seen in undisturbed spiral galaxies across the modern universe. But galaxies are not isolated. They exist within a larger cosmic context, and interactions with that context, with neighboring galaxies, with the hot gas of galaxy clusters, with the streams of material flowing along the filaments of the cosmic web, can trigger star formation in ways that internal processes alone would not. A close encounter with another galaxy can compress gas clouds and spark new star formation. A merger can funnel enormous amounts of gas toward the galactic center, powering a brief but intense starburst. Even the slow accretion of fresh gas from intergalactic filaments can sustain or reignite star formation in galaxies that might otherwise have exhausted their fuel. Both pathways are real, both are important, and the balance between them shifts depending on a galaxy's environment, its mass, its history, and where it sits within the large-scale structure of the universe. Understanding star formation means understanding not just the physics of individual gas clouds, but the full context in which galaxies live. And that context, when viewed from sufficient distance, is one of the most beautiful structures in nature. Think of a galaxy as a city. Not in a metaphorical sense that dissolves under examination, but in a way that genuinely captures something true about what galaxies are. A city is a concentration of activity, of light, of energy, of complexity, embedded in a wider landscape that is far less dense. Between cities there are roads and countryside and long stretches of relatively empty space. And cities come in different sizes, from small towns to vast metropolitan areas, each with its own character, its own history, its own relationship to the landscape around it. Galaxies are star cities. Concentrations of stellar mass and activity, embedded in the vast, mostly empty expanse of intergalactic space, connected to one another by the invisible threads of gravity and the structural filaments of the cosmic web. Like cities, they come in an extraordinary range of sizes. At the smallest end are the dwarf galaxies, tiny systems containing perhaps a few million to a few billion stars, far less massive than the Milky Way, often irregular in shape, sometimes nearly transparent in their low stellar density. Many of them orbit larger galaxies as satellites, caught in the gravitational influence of a more massive neighbor. The Milky Way has dozens of known dwarf satellite galaxies, and the true number may be considerably higher. These small systems are, in terms of sheer numbers, the most common type of galaxy in the universe. For every large galaxy like the Milky Way or Andromeda, there are many, many more dwarfs. At the other end of the scale are the giants, galaxies so large they are difficult to fully comprehend even in abstract terms. The largest galaxies known span more than 1 million light-years across. To put that in context, the Milky Way, which is itself a large spiral galaxy, spans roughly 100,000 light-years from edge to edge. A galaxy 1 million light-years across is 10 times larger in diameter, and many times more massive, representing the accumulated product of enormous amounts of galactic growth through mergers and accretion over billions of years. The current record holder for the largest known galaxy is a system called IC 1101. It is a supergiant elliptical galaxy sitting at the center of a large galaxy cluster, roughly 1 billion light-years from Earth. Its diameter has been estimated at around 6 million light-years in its most extended outer regions, making it roughly 60 times the diameter of the Milky Way. It contains an estimated 100 trillion stars. It is, by most measures, the largest single galaxy identified in the observable universe, a product of billions of years of mergers and consumption at the center of a rich cluster environment. Staring at an image of it with knowledge of its scale produces a particular kind of vertigo, the recognition that the Milky Way, with all its hundreds of billions of stars, would be a modest suburb of IC 1101. But IC 1101 is itself just one galaxy among an almost incomprehensible number. The total count of galaxies in the observable universe, the sphere of space from which light has had time to reach us since the Big Bang, is estimated at approximately 2 trillion. 2 trillion galaxies, each containing anywhere from millions to trillions of stars, scattered across a volume of space so vast that the numbers resist any intuitive grasp. That figure has itself been revised upward in recent years, as deeper surveys and improved analysis techniques revealed populations of small, faint galaxies that earlier estimates had missed. The universe is more densely populated with galaxies than previously thought, particularly with the smaller, fainter systems that are difficult to detect at great distances. 2 trillion galaxies. Each of them a city of stars. Each of them embedded in the larger structure of the cosmic web, connected by gravity to its neighbors, part of a hierarchy of groupings that extends from the smallest associations up to the largest structures the universe contains. At the first level of that hierarchy are galaxy groups. The Milky Way belongs to one, the local group, a collection of roughly 80 galaxies bound together by mutual gravity, dominated by the Milky Way and the Andromeda Galaxy, with the remainder being various dwarf and satellite galaxies scattered around them. Groups like the local group typically contain up to around 100 galaxies, held together within a common dark matter envelope, moving together through the larger cosmos. The next level up is the galaxy cluster, where groups contain tens to perhaps 100 galaxies. Clusters contain hundreds to thousands, all bound within a shared gravitational system and embedded in an enormous halo of dark matter. The gas between the galaxies in a cluster is not empty intergalactic space, it is filled with hot, diffuse plasma at temperatures of millions of degrees, glowing in X-ray light and containing more total mass than all the galaxies in the cluster combined. Clusters are not merely collections of galaxies. They are massive, complex systems in their own right, the largest gravitationally bound structures in the universe, where galaxy evolution is shaped as much by the cluster environment as by any internal process. The distinction between groups and clusters is not entirely sharp. There is a continuum of sizes, and the boundary between a large group and a small cluster is somewhat definitional. But the general principle holds. Galaxies are social objects, organized at multiple scales, from small intimate associations to vast metropolitan clusters. And those clusters are themselves not isolated, but connected to one another along the filaments of the cosmic web, arranged into superclusters and walls and voids that give the universe its large-scale structure. When we step back far enough to see that structure, when we look at maps of galaxy distribution across hundreds of millions of light years, what we find is not a random scattering. We find a web. Filaments of galaxies stretching across space, connecting at nodes where clusters sit, with vast empty voids lying between the filaments. A structure that was determined, in its broad outlines, by the distribution of dark matter in the early universe, and that has been growing and clarifying ever since. Every galaxy in that web has a history. Every group and cluster is an accumulation of that history, repeated across trillions of individual systems. The cosmic web is not just a description of where galaxies are. It is a record of how they got there, and of all the processes, formation, growth, merger, consumption, evolution, that shaped them along the way. From the first quantum fluctuations in the earliest moments of the universe, to the 2 trillion galaxies spread across the observable cosmos today, the story of how galaxies are born is ultimately a story about how structure emerges from almost nothing. How the universe, given enough time and governed by a handful of physical laws, organizes itself into something as intricate and varied and astonishing as what we observe when we look up at the sky. It is a story that is still being told, still being discovered, still being revised with every new telescope and every new observation. And it is, in the most literal sense, the story of where we come from. At the largest scales that astronomers can map, the cosmic web resolves into its grandest structures, the superclusters. These are the great mountain ranges of the universe, enormous concentrations of galaxy groups and clusters stretching across hundreds of millions of light years, the most visually dramatic features of the large-scale cosmic landscape. The Milky Way sits within one. Our local group is part of a larger structure called the Laniakea supercluster, a vast complex of galaxies spanning roughly 500 million light-years and containing the mass of hundreds of quadrillions of suns. When astronomers first mapped Laniakea in full, defining its boundaries by the gravitational flow of galaxies within it, the result was striking. A sprawling, asymmetric structure with the Milky Way sitting not at its center, but near its outer edge, on a minor tendril far from the dense core region known as the Great Attractor. But here is something important about superclusters that distinguishes them from every smaller structure in the galactic hierarchy. They are not gravitationally bound. Groups are bound. The galaxies within them orbit a common center, held together tightly enough that they will remain associated for the remaining life of the universe. Clusters are bound, even more massively so. They're thousands of galaxies locked together within dark matter halos of immense depth. But superclusters, for all their scale and apparent coherence, are not gravitationally bound structures. The galaxies and clusters within them are not orbiting a common center. They are not held together against the expansion of the universe. They are simply regions that happen to be denser than average, concentrations that formed from the same initial fluctuations that seeded all structure, but whose internal gravity is insufficient to overcome the accelerating expansion of space itself. The universe is expanding, and that expansion is accelerating. Dark energy, the mysterious component that makes up roughly 68% of the total energy content of the universe, is driving that acceleration, pushing space apart at an ever-increasing rate. On small scales, gravity wins. Galaxies, groups, and clusters remain bound. But on the scales of superclusters, dark energy wins. The Laniakea supercluster is not a stable structure. Over billions of years, its outer regions will be pulled apart by the expansion of space, its constituent groups and clusters drifting away from one another, the supercluster dissolving as a coherent entity even as the smaller structures within it remain internally bound. In a very real sense, superclusters are temporary concentrations, density fluctuations from the early universe that are coherent now but will not remain so indefinitely. They are the largest structures the universe will ever build, already at the limit of what gravity can maintain against the relentless push of dark energy. This sets the stage for understanding not just where galaxies are, but where they are going. The future of galaxies, like their past, is written in the physics of gravity, dark energy, and the slow processes of stellar evolution playing out across timescales so long that human history is not even a rounding error in the calculation. Within our own local group, one event in particular has been anticipated and modeled in considerable detail. The Milky Way and the Andromeda Galaxy, the two largest members of the local group, separated today by roughly 2.5 million light-years, are moving toward each other. Unlike most galaxies in the observable universe, which are being carried away from us by cosmic expansion, Andromeda is close enough that gravity dominates over expansion. It is approaching at roughly 110 kilometers per second, and the collision, when it comes, is expected in approximately 7 billion years. The merger of the Milky Way and Andromeda will be a transformative event for both galaxies. Their disks will interpenetrate, their stars will be scattered into new orbits by tidal forces, their gas clouds will collide and trigger powerful bursts of star formation. The event will likely unfold over hundreds of millions of years, a slow-motion catastrophe by human standards, but brief by cosmic ones. What emerges on the other side will almost certainly be a large elliptical galaxy, the orbital structure of both spiral disks scrambled beyond recovery, a new and different kind of object built from the combined mass of two ancient spirals. Astronomers have even given this future merger product a name, Melkomeda, or sometimes Melkdromeda. The naming is informal, but the physics is well established. Barring some highly improbable external disturbance, the merger will happen, and the night sky as seen from any planet surviving within these galaxies will be transformed beyond recognition long before the merger even completes. But long before the Milky Way and Andromeda meet, the universe will be changing in subtler ways. Stars are not permanent. They form, they burn through their fuel at rates determined by their mass, and they die, some quietly, as white dwarfs cooling slowly in the dark, others violently, as supernovae scattering their processed material across surrounding space. The stars burning today are the current generation, formed from gas enriched by all the stellar generations that preceded them. When they die, they enrich the gas further, and from that enriched gas, new generations of stars form. This cycle of stellar birth and death is the heartbeat of a living galaxy. It has been running for billions of years, and in galaxies where gas remains available, it will continue for billions more. Each new generation of stars forms from gas that is chemically richer than what came before, carrying the accumulated output of all previous generations. The universe grows progressively more complex, its matter progressively more diverse, with each turn of the cycle. But the diversity of galaxies is not only a matter of chemistry and star formation history. It is also a matter of form, and the variety of galactic shapes and structures in the observable universe is genuinely remarkable. Alongside the familiar spirals and ellipticals are galaxies that defy easy categorization. Ring galaxies, where a nearly circular band of star formation surrounds a relatively empty interior, likely produced when one galaxy passes directly through the center of another, driving a circular density wave outward through the disk like a ripple in a pond. Polar ring galaxies, where a disk of stars and gas orbits perpendicular to the main body of the galaxy, the product of a past interaction that left material in an extraordinary configuration. Galaxies with prominent warps in their disks, their outer regions tilted out of the plane defined by their inner portions, bent by the gravitational influence of nearby companions or by the asymmetric infall of material from outside. And then there are the jets. Some galaxies, powered by their actively feeding central supermassive black holes, shoot collimated streams of plasma outward from their cores at a significant fraction of the speed of light. These jets can extend for millions of light years, dwarfing the galaxy that produces them, pumping enormous amounts of energy into the surrounding intergalactic medium. Radio galaxies, quasars, blazars, the names given to various manifestations of this jet-powered activity, are among the most energetic steady-state phenomena in the observable universe. And there is another category that challenges intuition even further. Some galaxies are made almost entirely of dark matter. These ultra-diffuse galaxies contain relatively few stars for their size, so few that their stellar light is barely detectable, but their gravitational behavior reveals the presence of enormous dark matter halos. They are galaxies in the gravitational sense, concentrations of dark matter with some stars, but barely galaxies in the visual sense. Understanding how they form, why they failed to convert more of their mass into stars, and what their existence implies about the relationship between dark matter and star formation is an active area of research. The variety is extraordinary. The universe has not settled on a single template for what a galaxy should be. It has explored an enormous parameter space of sizes, shapes, compositions, and structures, producing a population of objects as diverse as the conditions that created them. That appreciation of galactic diversity is itself a relatively recent development. For most of human history, even the question of whether galaxies exist as distinct objects was unresolved. The fuzzy patches of light visible through early telescopes, some of which we now recognize as entire galaxies containing hundreds of billions of stars, were classified for centuries simply as nebulae, Latin for clouds. Their nature was unknown, their distances unmeasured, their scale unimagined. The realization that these objects were not clouds within the Milky Way but entire galaxies in their own right, island universes, as the concept was sometimes framed, did not come until the 20th century. In 1923, Edwin Hubble used the 100-inch telescope at Mount Wilson Observatory to resolve individual stars in the Andromeda Nebula, identifying a type of variable star whose brightness could be used as a distance indicator. His measurement placed Andromeda far beyond the boundaries of the Milky Way, demonstrating conclusively that it was not part of our galaxy but a separate stellar system, comparable in scale, lying at an enormous distance. That single observation transformed our understanding of the universe almost overnight. The Milky Way was not the universe. It was one galaxy among many, ultimately, as we now know, one among 2 trillion. The cosmos expanded, conceptually, by an almost incomprehensible factor in the space of a single measurement. The first spiral galaxy to be recognized as such was the Whirlpool Galaxy, known today by its catalog designation M51, observed by the astronomer Lord Rosse in 1845 using a massive reflecting telescope he had built in Ireland. Rosse's drawing of M51's spiral structure was the first time a spiral pattern had been identified in any extragalactic object, though at the time its true nature as a separate galaxy was not yet understood. That understanding would have to wait another 80 years, until Hubble's distance measurements made the scale of these objects undeniable. Within barely a century of Hubble's measurement, a century that spans less than a single human lifetime in the long run of history, we have gone from not knowing that other galaxies exist to mapping 2 trillion of them, resolving their internal structures, observing their formation in the early universe, and modeling their future evolution with sophisticated simulations. The pace of discovery has been extraordinary, and it shows no signs of slowing. The galaxies we observe today are between roughly 10 and 13.6 billion years old, nearly as old as the universe itself. The oldest among them formed when the cosmos was barely beginning, when the conditions that made galaxy formation possible had only just come into existence. They have been burning, growing, merging, and evolving ever since, through a history that stretches across nearly the full span of cosmic time. We are late arrivals to this story. Our Sun formed about 4.6 billion years ago, roughly 2/3 of the way through the Milky Way's current history. Life on Earth has been aware of the stars for only a vanishingly small fraction of that time, and has understood what they truly are for only the blink of an eye. And yet here we are, looking outward through the disk of a galaxy that began forming before most of the universe's stars had yet been born, trying to understand where it all came from. Asking questions that would have been incomprehensible to any previous generation of humans, and finding answers, imperfect, provisional, constantly refined, that are more astonishing than anything that could have been imagined before the tools existed to pursue them. The galaxies are out there, as they have always been. Ancient, vast, and quietly extraordinary. And the more carefully we look, the more they reveal.